Okay, welcome everybody. Everybody set to learn tonight?
Yeah.
We, if you don't mind, Father, I just want to ask you to help me teach and help everybody to learn. This is a tough subject, and we need your help. We pray these things in Jesus' name. Amen. Okay. Now I'm David.
Yes.
How did you do that?
Zoom is a powerful, powerful tool.
See,
I couldn't get my camera working, but I can get this avatar working. So this is what you're going to have to see tonight.
oh, all right. Well, good. That's actually quite cute. Anyway, let's get started. Tonight, we're going to talk about Ohm's law. But first, of course, we're going to do some review. Not talk, review about static electricity and electricity. So let's move on to that right away. Okay. Now, static electricity. Everybody remembers things get charged because things on themselves, they get ionized either with a positive charge or a negative charge, and you can develop quite a bit of voltage and reach out to touch a doorknob and you'll get zapped. That's what happens in the ionosphere, and that's chemically batteries like the battery that's in that picture there chemically ionizes things, and you get extra electrons on the negative side of the battery, and you get positive ions on the positive side of the battery, and current flows from the negative. The electrons flow out of the battery through the wire up through the lamp, and then continue on back to the positive pole of that battery. So if I'm going too fast, anybody holler. Okay, I want to show you.
Say, Joe,
Yes.
I have a question. I thought that last week or the week before, I heard that the electrons flow from negative to positive, but current moves from positive to negative. Is that correct, or did I hear that wrong?
Hang on just a second. Part of what you're saying is correct. Current flows in two different ways. There is electron flow, which is current of the electrons flowing from the negative to the positive. And then there's conventional flow, which is the holes, which I'm going to demonstrate here very shortly, that flow from the positive to the negative. W7. I know it's a brain teaser. But let me.
Are you saying then that current electron flow and current flow are basically the same?
No, they're both. You can either look at it from the hole flow or from the electron flow. Here, let me. I'm just getting ready to show this, so let me do this. Do you remember this? Anybody?
Yes.
Yeah.
Okay, who was asking the question?
I was.
Oh, okay. All right. See our battery here? Now remember this battery's in here backwards, but ignore that. Got a switch. We got a resistor for a load. And we come through here and we got a wire with a bunch of electrons on it, and we flow back to here. So if we're going to look at electron flow, you got a negative charge here and you got a positive charge over here. This electron is negatively charged, right?
Right.
So it's going to get attracted to the positive, which leaves a hole. And then the next electron is attracted to that positive hole, which in it flips over like this. Imagine all these having atoms, and electrons are flowing from one atom to the next. So here's
But
a hole in an
isn't
atom.
isn't that first hole though just a lack of an electron in that atom?
Correct.
So it's not really a space traveling to the left.
Well, yes, I mean,
It's one electron moving from one atom to the next, because of that that positive charge, that positive ion.
right. Well, you can think of an atom as having a hole because the electron's missing.
Okay,
Does that help you?
that does. Thanks.
Yeah, okay. So anyway, we've got the hole that's a positive charged electron, or not electron, atom. And the electron that's on the next one is attracted to that hole and it moves over, producing another atom here that's minus an electron, which makes it positively charged, which attracts the next electron, and so on and so forth. Now, this is electron flow. If we look at the beads going across, that's electron flow. But if you look at the hole that's moving, that's hole flow. And that's conventional current flow going this direction. And folks, both ways are used. And I honestly, I grew up with electron flow, and that's much easier for me to understand. But a lot of the stuff that we're working with will be talking about hole flow. So anybody's mind smoking yet? Yeah, well, I can understand why.
Well, my basic question was, are you using current and electron flow interchangeably? When you say current flow, sometimes you say electron flow.
Yes.
So those are interchangeable terms.
Correct.
Okay, I'm good.
Either talk about conventional, which is the hole flow.
Well, that's another thing.
Or electron flow. Unfortunately, a lot of engineers, they learn this through mathematics. That's all they know is mathematics. They do not understand what is really happening. And they figure out everything with mathematics. It's kind of a sad state of affairs, but they do that. But we want to understand how it works. And we're talking about an electron flow. And I do, but we're going to run into circumstances where we're talking about hole flow, which is the positive charges moving that direction. Any questions about this? This is something to demonstrate electron flow. And John was very kind to come over this afternoon and help me film this. Okay. This is our demonstration with water flowing on the right-hand side of the screen there. You see it? Now John is going to crunch on the resistor and turn the water off. Did you see it turn off? So by increasing resistance, you reduce the amount of flow. And we can pretend like the water spraying out there is electrons.
That's
So
what
here,
a choke does, sort of.
actually it does. But this is we're right now we're just talking about DC. So now watch, he's going to crimp it again. And you can see on the left side, that's E, electromotive force or voltage, and you can see the pressure in the gauge. Now he's crimped it off and he's reduced the amount of water flowing through there. See how it's just spitting out there a little bit? And then he will release it again. So there's our current. I is current, remember? Our electron flow. Now watch this. Watch the meter on the left. See the voltage drop? And then watch the water on the right. It's okay, we got, the voltage is dropping off and the current's dropping off. And the resistance is staying the same. Did everybody see that, or would they like to see it again?
That's interesting.
Would anybody like to see that again? No?
No, thank you.
No.
Good job, John, though.
Oh, well, yeah. So, couldn't have made it without you.
Yeah, John was, and Janet was behind that black curtain holding it up.
Good job,
We had
Janet.
white in the background and
Couldn't see
the
the
water didn't show up. So the water here is our electrons flowing. You know, imagine a drop of water. Well, here's, when this thing's flowing, I mean, thousands of drops of water are going at once. Well, when it comes to electrons, millions, billions, trillions of electrons are flowing. So now let's see. Can I go on to the next one? There we go. Current flow in parallel circuits. Okay. Back to the camera. Here we have a battery. Right here. And this is going to be a 5-volt battery. Anybody ever heard of a 5-volt battery? They don't exist, but I'm using 5 volts because that's what our little power supply puts out. Okay, and then we go through a switch. And here we have a 100 ohm resistor, another 100 ohm. Oh boy, I'm shaking too much. And another 100 ohm resistor, all hooked in parallel. Now, can somebody tell me what the total resistance is of those 3 resistors in parallel?
33.
Yeah. Go, John?
I said 33, but I think it is closer to what Scott said, which is 35.
Actually, it's 33.3333.
So in a row, yeah. Okay.
3. Get the picture? Anyway, it's 33 ohms. So current, this is the negative side of the battery, and this is the positive side of the battery here. So everything up here is positive, right? That's not a very good, oh man, is that, I'm shaking too much. Okay, so this side down here, everything is negative. So at this point right here, this is the minus. Well, this is the minus, which if we had a voltmeter here, and we had the minus and we had a cord and we had it hooked to right here, and we took the positive and we went up and touched it on here, it reads 0 volts because it's on the same line. It's everything. But if you put the voltmeter up here, then it would read 5 volts. So we got a 100 ohm resistor with 5 volts across it, and we got 3 of them in parallel, so we got 33 ohms. Now we're going to be going into Ohm's law, and we will be able to know how much current is going through this resistor, how much is going through this resistor, and how much is going through this resistor. And what is the total current going to be? Somebody want to tell me? It's
150 milliamps.
No. I equals E over R. This case, E is 5 and R is 33. So 5 divided by 33 would be 50, 3.1. I want to say 0.15. I'm not sure if that's the exact amount.
150 milliamps.
Correct. Which is, remember our little 78L05? What was its current rating? Anybody remember?
It was 50 milliamps.
It was 100. It was 100 milliamps, so this would damage that thing eventually because it would overheat. So that's resistors in parallel. Current goes this way, and this way, according to whatever the resistor is. And then they all combine. And so they all are, the current that is here is the same as the current that's up there. And it divides in each one of these. All right. Now, resistors in series. Here we got a plus, the minus, and again 5 volts. We got 100 ohm, 100 ohm, and 100 ohm. So that makes, what is the total resistance? Somebody?
300.
300 ohms. John. Good
Yes.
answer.
What?
Good answer.
Oh, thanks.
We're learning here, folks. So the current comes, we got a bunch of electrons down here, right? And we got a hole up here. Well, if we got an electron here, it's going to be attracted to this hole, which will leave a hole here. And so if we got an electron here, it will be attracted to this hole, which will leave a hole there. A hole here. The holes are positive charge, and the electrons are negative. So we've got a negative, it'll be attracted to this hole. Following me? So the current just goes, the electron current goes this direction, around the corner, and it goes through each one of these resistors. Now, can somebody tell me how much current is going here compared to how much current is going through here compared to how much current is going through there?
All the same?
All the same. Every single one of them. They all, because they're all hooked up in series, the current is the same. So when we figure this out with Ohm's law, we'll know what the current is. And so we got 300 ohms at 5 volts. I is equal to E over R, which is equal to
0.017.
0.017 amps, or 17 milliamps. Good call, Scott. Now, yeah, I forgot one thing. I had to throw it on the floor where I could hardly reach. What? I can't even move that. The thing that Daron demonstrated last week is that each one of these helps divide the voltage. Since there's 3 resistors here in series, if this is 5 volts, and each one of these is equal, so this will be at this point right here. If you've got a voltmeter, oops, I'm off the screen here. If we have a voltmeter, now we got the negative terminal here hooked up here, and then we take the positive terminal and we come up here and we measure this point right here. What's going to be the voltage? I know that you can't quite easily do that in your head, but it'll be 1/3 of 5 volts. And I'm just going to call it 1.7, that's close enough. So the voltage across this resistor is 1.7 volts. And since the current going through here is the same, this voltage here, from here to here, will be 1.7 volts, or this will be 3.4 volts. And then if you measured from here to here, this is going to be 5 volts. And don't worry if you're not getting this yet, because we're going to cover this in more detail. I'm just trying to warm your brain up. Now, the reason we do voltage dividers is for something like this. This is a transistor. Here's our battery, which has 5 volts on it here. So we got +5, and we got minus down here. So the current will come and go through here and through here. Now this is 1,000 ohms, and this is 1,000 ohms. So somebody tell me what the voltage is right there. 2.5 volts. The transistor draws very little current, so it should make little difference in what this voltage is. Now, this is a transistor right here. It's an NPN transistor. And notice this arrow right here. It's pointing away. Darren, what was your, you had a term for that to help you remember it.
Not pointing in, NPN.
So the arrow is pointing out, so it's not pointing in. That makes it NPN. If it's pointing in, then it's PNP. But this is a junction indicated by this. You can also do diodes, which look like this. That's a junction. Hole current is going that way. Electron current cannot. Electron. Sorry for my writing. Oops. Electron can't flow that way. But hole flow can go that way. So that's a diode. This is being a transistor. So anyway, this is the reason that we're learning about voltage dividers, so that you can understand how circuits work. Now,
Can I see that again for a couple seconds? Just a second.
Scott. Why are you throwing them on the floor?
because I don't have any other place to put them. Okay, Scott, go ahead.
Okay. And what was the resistor on the transistor there, on the top and bottom?
These here.
Yeah.
Okay, now, mind you, I just made those up.
Okay. All right.
This, I have thought about setting this up and see if it will actually work. Because at this point right here, because that's we're going to call it a silicon NPN transistor, which means this junction here drops about 0.6 volts. So this point right here will be 1.9 volts. So because this is a fixed voltage, let's see, I equals E over R, right? So we got, which is equal to 1.9 volts right here, 0 volts here, and 100 ohms. That means it's by 100, which is equal to 1.9 milliamps. Did I have that order of magnitude correct? Yeah.
Yes.
So the current going through this transistor is 1.9 milliamps. Which means if you have 1.9 milliamps up here, you could use Ohm's law to figure out what the voltage is here. And then the transistor makes up the difference.
1.9 divided by 100.
Yeah. Should be 0.0019, I think.
It's 0.019.
0.019.
Yeah.
Uh-oh,
19 minutes.
19 milliamps. Any more questions? Current flow in a series circuit. Oh, all right, done that. We've done this. Okay, now into our main subject for today. Now, this is not, I'm going to tell you what resistors are and how they look, but I'm not going to talk anything about what they do. I wanted to show you this because last time, or the first class, I showed you what resistors look like. Some big ones like this. And some more down to earth ones like this, which are still used in some things. The one thing I didn't get out was my resistors. Now the resistors that I showed that are on this page are called surface mount resistors. In our old stuff, we used to use these. These kind of resistors. Now we're going to be talking about power. And when I first talked to you, and I made a mistake and talked about power, but this resistor will handle 2 watts. If you put a voltage across it, it'll draw so much current. And watts is current times voltage. But we're going to get into that in more detail later. So here's a 2 watt, here's a 1 watt, and here's a 1/2 watt. And some of the resistors that are in your package are 1/4 watt. But when you get into surface mount resistors, these little guys here. Now I want you to see the size. I mean, here's my finger, right? This is kind of a big one. I used to have a lot of these, this size right here. Does anybody see that little dot? Yeah. I had to replace one, so I ordered a set. It seems to be, it cost me like $10, $12 for several hundred resistors. But I think that's a 47 ohm resistor. And it's a tiny thing. And when you get them, they come in strips like this. This one up here is what came out of this package. This one here came out of this package here. And they have machines that automatically just peel these things open and take them out. And then this one here, which was another one I needed to be able to handle that power. So I had to get a bigger surface mount resistor and solder it in. But it's that size there. Now, I want to show you this resistor. Now this is a 2 watt resistor, and I just wonder if I can get down here a little closer. I think. Yeah, there we go. Okay, this is a special one. It's a Joncas resistor. I've modified it. Oops, how am I going to do this? Now I'm going to touch this right here. Oh, hold still, dang it. Okay, it's reading at about 12,000 ohms. I'm going to move to about the middle. I had an easier time with my fluke. I'm kind of prejudiced. Oh, come on. Now let me try this.
There you go.
I told Daron that I was going to do this. He thought, oh, well, that's going to be cool. Okay, that's
It's cool.
7,000 ohms. And then as I move down here, I get down here at this end. Come on, don't make a liar out of me. 6,000 ohms. You can see as I go across the carbon here, it gets less and less and less as I go from this end down to this end. But there's just carbon in here like pencil lead. And that's how resistors are made. They have carbon built up that has X amount of resistance per length.
Where's your other lead?
In my hand here.
Oh. I was like, how's he doing that? That's magic.
So in theory, you could make a resistor anything you want. As far as
Yes, you could.
by using
That-
graphite.
Yeah, yes, you could actually take pencil lead and make a resistor.
Thank you.
Here is a power cable. This is an ICOM cable. And I want you to notice these fuses. This is a resistor. Believe it or not, this resists the electricity. The radio that this was hooked up to when you tried to transmit, it would not put out its full power. And that's because these, I want to call them, they're really cheap fuses. See that little tip on there? It just touches the end of this fuse. And then the other end looks the same. Oops, I can't push it out. I used to be the fuse engineer at Tektronix. When you purchase a cable, first of all, the fuses are there not to protect the equipment. The fuses are there to protect the wire. If you have these hooked up to a 12-volt battery and this whole thing stretched out through your car and something shorts at the ground, with the fuses here, they're not going to blow it. What it's going to do is it's going to burn up this cable and your car. These things need to be at this end by the battery. And don't use this style of fuse. I mean, I can't tell you how many fires. I mean, I used to work on boats and people would stick a wire in there, hook it up to the battery, and then they'd have a fuse at the other end for the radio or whatever. And they'd burn their boats down because something shorted that cable. And a battery, you know, a 12-volt battery for an automobile or a boat or anything else, it'll easily put out 1,000 amps. And when you got that running through a hunk of wire this size, the wire gets hot because it's a resistor. There's probably, normally, this is number 12 wire, normally from here to here, there, I'm going to guess there might be 0.3 ohms, 0.5 ohms. But if you start going 0.5 ohms up and 0.5 ohms back, and you draw 20 amps through it, oops, I think I'm an order of magnitude out in that. So if you are having power issues, check your cable and check the voltage at this point, at this point right here. Get some probes, you can pull this back. And you can stick your probes in here and measure the voltage actually getting to your radio. If you start out with 13.8 volts and you don't end up with 13.2 or so at the radio, you're losing too much in your cable, because your radios are rated at 13.8 volts for 100 watts. If it's at 12.5 volts, it's not going to put out 100 watts. And if it's at 11 volts, it's not going to work.
So before you go on,
Yes.
what is your choices there? If you find yourself in that situation, go to a bigger fuse?
No.
Yeah, you
But the
decide.
fuse, make sure your fuse is by your battery.
Yeah, first
So
of
it's a
all,
location thing only. Okay.
I tell you what, and somebody, John, you can hold me to this.
Okay.
Next time I will bring fuses and fuse holders that are. Somebody needs to mute their audio. Anyway, I will bring the proper kind of fuses. And actually, I will, if I can remember, I will try to include an actual installation on Willie's vehicle that we did, where we put in fuses at the battery. And we ran for a HF rig that's going to be running 100 watts. You need to run at least number 10 wire. Most times, number 10 wires from the battery to the cockpit, which is about 6 or 8 feet, is fine, and you won't lose that much voltage. But the fuses need to be at the battery, because when you run that wire through your firewall, if something goes wrong and it gets shorted, it's going to burn up the inside of your hood, and it won't be a pleasant thing. So, and it's also a good thing to fuse both sides, and I'll explain that another time. Now, I want to talk about voltage sources. Just in general, take a look at that thing right in the middle of the picture. I think that's Grand Coulee Dam. And that is where many people in the United States gets their power from, that California, Arizona, Nevada, from that dam. And they're, okay, let's see, does my mouse show up?
Yes.
It does.
It's over the place.
Yeah, and here's an AC outlet, 120 volt AC, and it comes from something like this. So we take this and we plug this into it, which is our typical power supply for our ham station. I highly recommend this style of power supply for your station. They weigh a ton, and but they put out little noise. We're going to learn about switching power supplies later. Some of them are good, some of them are really dirty and they make a lot of noise, RF noise, which gets into your radio. Of course, here's a 12 volt battery from a car. Here is a schematic diagram of a battery source. Here's a AA battery, just an alkaline battery. Here's a battery over here, indicated with, could be this here, and with the load. So, and then there's this battery here. Potato batteries. You take dissimilar metals and you stuff them into the battery and you cook them together and you end up with enough to, see that little light there lit up? So you can have all kinds of voltage sources. Now we're going to talk about Ohm's law. George Ohm came up with this quite a long time ago. Here's a circuit that we're familiar with, a battery, And then we have, now notice the I here and notice the way the arrow is pointed. What kind of current are they talking about?
Conventional.
Whole flow conventional, correct. And there's a resistance, so the whole flow is going this direction. And it's flowing in a closed circuit. Electron flow, which is the negative ones, they're going this direction. So I, which is current, is equal to voltage over R. Now, I love this little diagram. This guy's voltage, and he's the one pushing, right? And then we got this guy here who's the resistor in ohms. He's the one putting the squeeze on the wire that the amp is trying to go through. And he's keeping the amp from moving. So if he's got a real tight pull on that, it'll make it really hard for the amperes to go through the wire. Is everybody getting this? Okay, now this is a way to remember Ohm's law. And here in a moment, I'm going to show you 4 others. What I recommend is you go online, you go to Google search or your search engine, type in Ohm's law, and then click on images. If you want to know what the voltage is, you multiply the current, I, times R. If you want to know what I is, the current is, you divide the voltage by the resistance. If you want to know what the resistance is, you divide the voltage by the current. So I is equal to V, or I say E over R, E being the electromotive force, V is equal to IR, and R is equal to VI. But here, now look, now watch this. Here's another one. I like this one because it shows E in voltage, I in current, and R in resistance. Okay, and then there's this one here that shows them all separated out. And then there's this one here. See how they're doing that? And then there's this. I like this one because it puts it all together. And here momentarily, we're going to be talking about power. So here's the normal sign. Here it is showing the what each one stands for. Here's the actual circuit. Here's a battery, a resistor, and they're showing the voltage across the resistor and the current. And here's a device for figuring out current, resistance, voltage, and power. And this is they have literally dozens of these things online. You pick out one that's your favorite color and use it. So now I'm going to, nobody has to know who Kirchhoff is. But Kirchhoff came up with a bunch of laws. And here's a voltage. We're going to say that this is 5 volts because that's what we've been experimenting with. This is showing what type of current flow are we seeing here?
Conventional.
Conventional, thank you. Or if we wanted to, we could talk about the electrons that are down here, and then they would be going this direction. But notice we have a closed circuit. The current is the same in every single spot in this closed circuit. As long as everything's in series, the current is the same. So if R1 is 100 ohms and R2 is 100 ohms, what's the total resistance? 200 ohms. And the voltage we'll say is 5. What's the current? Rose, are you calculating?
No,
Oh, you're not, no. I thought you were
I
calculating.
thought about it. I'm brain dead.
All
Is
right,
it
all right.
25 milliamps?
Is that, E is 5 divided by 200 equals, right, 25 milliamps, 0.025 amps. So if the current's the same in every one of these, what's the voltage across R2, which is 100 ohms?
Mhm.
2.5 volts. What's the current across R1? Did I say current? I meant voltage. Correct. So what is the voltage if you got your negative lead here? What's the voltage right at this point here? 2.5 volts. The battery has 5 volts. The sum of this out here has to equal 5 volts. So we got we have 2.5 volts across here, and we have 2.5 volts across here. Negative to positive, negative to positive. So this adds up to plus 5 volts, which equals the 5 volts that struck the battery. Kirchhoff came up with a whole bunch of laws that are very effective. And we'll discuss that in general, but we won't really treat them as laws. So moving on to our next one, power. Power is actually the current times the voltage. Well, good timing. It's either IE, which is I times electromotive force, or IV, which is I times voltage. Electromotive force is measured in volts. I learned I equals E over R. Today, most people use V. So going on to the next, watts. Watts is a place in Los Angeles. And I want everybody to remember that. Go on, nobody laughed? Power is everything. Whenever a resistor is being used, it dissipates power because there's voltage across it and current going through it. So if power is
Everything.
everything, right, it is the voltage times the current. And in a resistor, it only, if it's power, it dissipates it in one way, and that's by turning it into heat. That's why you have those huge resistors that I showed you, and smaller ones, smaller ones, and smaller ones. So if you're working on something and you find a resistor that's been burnt, don't put a smaller one in, because it'll just burn up as quick as the first one did. So fix the problem and then replace it with the proper size or bigger. Power. I showed you a power supply that's used in amateur radio stations earlier. That's where we get our power from for our amateur stations. The amount of power that is radiated from your antenna, it's actually a voltage and a current. When you have a radio wave going out, there's a voltage portion to it. And well, actually it's somebody help me out. It's a magnetic field, which is associated with current that's perpendicular to it that goes out. So that is the power that actually gets radiated from your antenna. When your handheld radio says it has 5 watts, we can assume that's 5 watts output to the antenna. So your antenna should radiate, if it's a proper antenna, 5 watts. How much power does your handy talkie put out. Most of them are 5 watts. And then a lower one like a watt, and then down in the milliwatts. So if you're near somebody, you just set it to a few milliwatts and it'll function. Okay. Now, here's another one of these devices. Here's E, electromotive force, or B. Here is R for resistance. Here's I as current, and here is P for power. Now notice it says E times I. But E can be replaced with power. Oh, wait a minute. R times I. So E, power can also be, you can replace the I, oh shoot. You can replace the E with
R times I.
R times I. Thank you, Scott. I'm getting tired, and we're almost done here. And we're going to have our break in just a moment. So Daron is going to give us some wonderful illustrations on how this works. So I found this one, and what I liked about this one is it explains P is for power, E is for electromotive force, which is volts, and so on and so forth. So I believe, Daron, you're on in 10 minutes. Let's take a break.
Well, I hope you're going to tell me what to do.
So you got R times I is
Yeah. R times
R
I
equals I squared.
Okay, Daron.
All right, Joe, what'd you want to do? I have a light bulb.
Oh, good. Well, I wanted you to illustrate power. And
variable power supply.
yeah, variable power supply. Yeah, don't burn the bulb up yet, quite yet.
I have a spare, but it's interesting. This one, there's 18 volts,
Whoa,
19.
He's gonna make it.
What's it
20.
rated at?
I don't know. It's an automotive tail light.
it's 12 volt.
Oh, okay.
Well, they,
22,
Keep going.
23,
Go. See if you can go. A little more.
24, 25, 26, 27, 28.
Yeah,
Is it getting hot? Should be getting hot.
Real hot.
It's warm, 29 volts. It's a 30 volt power supply. So that's about it. It's drawing 3/4 of an amp.
holy cow.
I thought it would just blow at, like 25 or so, but no.
Well, I used to, believe it or not, my specialty at Tektronix was switches, and I also had light bulbs. And the
Well-
life of a light depends on the voltage. If it's a 12 volt bulb, or it's running at 13.8 volts, and
Right?
then you put it in and it's running at 14.8, which sometimes they would, it really shortens the life of the bulb. And the same thing with filaments on transmitters. If you're running the filaments a little bit higher voltage than they're designed for, it'll really shorten the life of the tube.
Well,
So
that's
if you run it slightly lower than it's supposed to be, it really extends the life of the light bulb. Are you
That's
trying to burn that one up too?
32 volts there, and it just is hanging in there.
Wow.
Hey, you were supposed to burn something up, Daron.
Oh, I'll burn something up next.
But this is an illustration of power.
So at 13.8 volts, that is 265 milliamps, and just over 3.5 watts of power.
Okay. Can you actually see watts on your meter?
Yes.
Okay, well, crank it down to 1 watt.
Oh, okay. That would be at 6 volts.
6 volts and, how many,
Point- 0.166 amps, so 166 milliamps.
so it'd be 0.16 times 6 volts would equal 1 watt. Okay, crank it up to 2. We can see it's brighter.
Well, there's 2 watts at 215 milliamps.
I should get out my calculator.
I can just read it off the meter, save you all that trouble, Joe.
Oh, yeah, okay. Okay, we'll go back to 12.6.
12.6 volts,
Yeah,
252 milliamps.
go
Three-
to 14.2.
270.
Now that would be 14.2 volts is typically what your alternator in your car is running at. So if your car's running and you got your tail lights on, that's how bright it would be. And that's actually what the bulbs, when they say it's a 12-volt bulb, it's actually a 14.2 volt bulb.
Yeah, rated for that standard DC bus. Yeah.
Yeah.
I just can't kill it, at least not at 30 volts.
Well, if you left it on bright enough, it'd probably burn up quick enough, but that's cool. Well, do you have anything else you can burn up?
I can burn a resistor up for you.
Yeah.
Well, let's do that.
A few people are
You
sick.
got it instructed tonight.
Yeah, but get a resistor that you know what the wattage is.
Well, that's the fun part, Joe. Here is
Is it
a
quarter watt?
quarter watt. Let me see if it'll reach under the other thing here so you can see the smoke better.
Oh, we can't see it at all.
You just went off camera.
Hang on.
Oh,
Oh,
there you
All
go.
right.
There you go.
sorry.
So we'll start.
Oh. Crank it up to a quarter watt first.
Oh, nothing's going to happen there.
Well, of course, but we want to see if it gets warm at all. I want
Okay,
to see
so
if
that's-
you can burn your finger.
1.8 volts. I'm not going to keep testing it that way for you, Joe.
Was it warm?
Nope.
Wasn't warm at all. Okay. Now,
So
yeah,
there's
we
3
can't-
volts.
We can't quite see it, Darren.
Oh. Oh, it's starting to warm up there. 3 volts, 300 milliamps.
How many watts?
0.97, so almost 1 watt.
Is it blackening? Nope.
Nope, not yet. It's warm. Let's run it up to 6 volts. That's 628 milliamps, 3.7 watts. There's a little smoke.
Oh, okay, it's smoking.
Yeah.
Oh, yeah.
Woo!
All right.
Yeah.
Success.
it's- Now getting that smoke back in there is really tough.
I guess.
Toothpaste and a
Joe will show you how to do that.
Gee, thanks, Darren.
That would make more carbon.
So that was quite a bit of smoke. I wonder, let's just check it now. You think it's dead?
No,
Yeah.
No,
no,
I don't think it is.
Well, it's not going to be the same resistance.
that's true.
Oh, ye of little faith.
Well, what was it originally?
It was 10 ohms,
Woo, look at that.
Holy cow!
which is where it is.
I can't believe that.
So even though we let the smoke out and hang on, can't really see that. It's discolored enough you'd have a hard time reading the color bands on it at all.
Mhm.
it's still registering 10 ohms.
Well, that's really unusual.
Usually when you see them smoked like that, that's a problem.
I'll bet you can't get the same kind of current through it.
Oh, is that a challenge?
That's a challenge.
Yeah,
All right, well, let's see what we can do here. There's 4 volts, 400 milliamps. 6 volts, 600 milliamps. We let all the smoke out already.
Well, that's pretty amazing. What kind of resistor is that?
There we go.
Glowing red.
Smoking.
Found a little more. Yeah, there we go.
Oh, yeah.
8 volts.
oh,
and
that
it's-
baby's lighting up now.
I guess.
Well, it looks like it's blistered in the middle.
Yeah, I think it's probably shot now, but still, still not open. I'll tell you that.
Yeah, tough resistors. But folks, the idea here is to show you that you have to be aware that you don't put too much voltage across a resistor and exceed its power rating. Because you can burn them up. And sometimes when they burn up other stuff with them.
Mhm.
26 ohms now.
Yeah.
Yeah, I think
Thank you for sacrificing that resistor.
Amen.
it's not the resistor, it's just the smell of it now for a couple of days. Yeah, I was surprised that it lasted that long.
Yeah, me too.
He needs a little Chanel #5 there.
It just reminds me when you're looking at a circuit board for a problem and you see that, you instantly go to that as potentially the problem. It just indicates that whatever is downstream from there drew more current than it should have.
Correct.
So it may not just be that component. You have to look at the rest of the circuit and see what it was that it was feeding and why that drew more current than necessary.
Okay. Well, are you
Right.
ready for your next assignment?
Yes.
And I want you to burn up a 78 LO5.
You think we can do that?
I think we might.
Well, I have to find it first.
Do you have more than one 78 LO5s?
No?
Oh, okay. Well, I get you half dozen more.
All right.
Started.
Are you thinking we should do that? How do you want to do that exactly, Joe?
Well, what I would do is I would take the the connector for the 9-volt battery
Yeah.
and hook it up to your power supply.
Okay.
Because I don't know that the 9-volt battery will put out enough current to smoke something.
It'll get it mighty hot, I'll tell you. Just that 9-volt battery. Cause it did on mine,
Did it?
yeah.
Yeah, Scott says he can get it mighty hot.
Well, we'll see. I think we have to have a switch in there still somewhere to complete this circuit, right?
Oh, that could be so much more fun.
No, I think it hooked up the
Just burn stuff.
12 volts to that terminal. That
Yeah. Gotta cheat a little bit here, get some places to do that.
Oh, you're gonna do it that way. Oh, okay. I was gonna have
Sorry.
it hooked up to that. No, that's fine. Have at it. Whatever your preference is. Yeah, he just took the resistors in there to So you'd have something to hook to.
Yeah, we're not going through them. We're just using the lead part.
Yeah, now, I can't remember the specs, but you can go ahead and crank your power supply up to 12 volts.
All right, we still got to add
13.8 or 14.2 or
another jumper in here somewhere, don't we?
I don't know. I can't quite see how everything is.
Oh,
There you
it's
go.
there.
Okay, well, now what you need to do is put enough load on it to cook the
Well, we're on.
LO5.
Yeah, you need current now.
You
Yep.
know, just for information, the spec sheet on the 78 LO5 is 100 milliamp.
And we're drawing
Ours
60.
are, pardon?
We're drawing 60.
60 milliamp right now? Okay. And the next size, your 7805, which is lying just above there, is rated for 1 amp, probably. Although some of them are only half an amp, some of them are 1.5 amps. But so when you're dealing with really small currents, use a little 78 LO5. But if you start drawing more current, then you're going to want a larger device to do it. So hopefully, what we're going to do is burn up the 78 LO5.
Let me see if I've got another jumper. Well, we can put a ammeter in series with the output, I think, here. So I was looking at the power supply, Joe. So we're actually drawing 100 milliamps, 98.
What are we charging, a capacitor or?
No, I just surged a little bit to start with, I guess.
Oh, okay. So what do we got? 2 resistors or?
3 resistors.
Oh, the 3 resistors. Oh. So do we know what the actual voltage is? Before, when we did this, you were able to maintain 5 volts.
Oh, we're 5 volts out of the regulator, yes.
Okay, so if we take 5 volts from, where do you got your power supply set at?
13.
13? So
Yes.
5 from 13 is 8 volts at 60 milliamps. Is it hot?
Yes, it is.
Okay.
Just took me a second to check, but yes.
Okay. So
So we could crank up the input.
okay, well, let's say 8 times 0.06 equals, that's a half a watt being dissipated by that little device. This device gets rid of the extra voltage by dissipating it as heat.
Mhm.
What voltage are you at now, Aaron?
I'm at 15.
The current's dropping off.
Yeah, I'm wondering if that's just starting to fail
Can
in the
you measure
regulator.
the voltage and see if it's folded back?
Well, the LED's still on, so I'm going to guess it
Yeah.
hasn't.
But did it brighten though, the LED?
Well, what's the question, Scott?
Did it brighten? I
It
thought I
just-
maybe saw the
it just
LED
did.
brighten a little bit.
It just did.
Yeah.
Now it's going down again.
Mm-hmm.
Yeah, it's going down as I crank the voltage up.
What voltage are you at now?
I'm at 15 again.
Yeah, I'd kind of like to know what its output voltage is.
Well, that might require another meter. Which might be within my reach. Hang on. No, I guess not. All right, so we'll get rid of this ammeter thing we're doing. But measuring the current. And you want to see the voltage on the output of the regulator.
Correct. 0 volts.
Well, we killed it because the LED went out.
Did you get it plugged into the right place?
Well, that's what I'm wondering too. Oh, something's not
Oh.
making a good contact. There we
Oh,
go.
there-
There's
Yeah, there's the,
Lights.
LEDs.
well, that wasn't
Okay.
over.
Now we're just loading down that much. Yeah, that meter just loads it down.
Well, you still got in the current position?
No,
Meter?
oh, I still got it on the current plug though. Good call, Joe. That's why I burn things up.
Well, there we go. Oh, we're down to 1.5 volts.
Hang on, hang on.
Yeah, see, it has folded back, I think, to protect itself. I think if you drop the voltage input, the voltage will come up. Is that what you're doing?
Yes, sir. I am back down to 9 volts.
But it's still not putting out its 5 volts.
Nope. Let's grab it over here though.
Well, let's try reducing its load to something it should have. Take out 2 of the resistors.
Joe,
Yes, Scott.
you know, the way I got mine to warm up nicely was
Nicely.
I just put you know, your standard circuit there, and I put together, the 3 resist 100 ohm resistors in parallel
Yeah.
on that, and that gave me 0.15 amps, and so I was 50% over.
Yeah. Yes.
Oh,
Look at this. He took out the excessive load and it went right back up to 5 volts.
Yeah.
That's one tough little device.
it is.
Man, that's amazing.
Yeah, I just varied the voltage up to 13 volts and it stayed there.
Wow. Well, I don't know who the manufacturer of that is, but that's to me pretty amazing. Now you're overcurrenting it again.
Yeah, won't do it.
And I'm not sure, I might need to look at the spec sheet and see if it's designed to fold back. Because
Well,
a lot of the power supplies, if you try to draw too much current, they just drop the voltage to their maximum current they'll put out.
Mm,
Are you following what I'm saying?
yeah.
Yeah, I'm kind of surprised this one held up that well.
Yeah, well, we tried to burn it up and it didn't work. Well, congratulations. Well, honestly, Darren, I don't have anything else. Anybody got any questions or?
I know in tubes, as the years go by, they get older and they will break down. Will these critters break down over a number of years?
not normally. Not if they were designed correctly.
Hey,
Yeah, tubes emit electrons. And the cathode, or the filament and or the cathode, which emits the electrons, eventually you will strip all the electrons off of it. It takes a long time to do it, but then the tube becomes flat. It won't put out the current it's supposed to.
any way to reincarnate those critters or put them in the trash can?
Actually, sometimes you can actually heat the cathode really hot by increase, like had that light bulb and he increased the voltage to it. You increase the voltage to the filament to 10-20% over. I'm not sure exactly how much, I've forgotten. And then the filament gets real hot and it will actually bring more electrons to the surface. And you can rejuvenate tubes that way. In fact, it used to be when you had picture tubes in TVs, when the tube would get worn out because it's been used for so long and the electrons aren't able to get out anymore, they had rejuvenators that would put a high voltage on the filament and apply a voltage and they'd draw electrons to the surface. And sometimes you can make the tube last a little while longer. Little while. Not too long.
Like to finish the shell or?
Yeah. Well, usually you had to have your electronic technicians come over.
It makes you,
Do
what,
it for you.
extra couple of months to do it or something like
Yeah,
that.
yeah, it delays the inevitable.
Good way to put it.
So, well, I'm happy with what we've done here tonight.
Yeah.
Anybody got any suggestions on stuff that we can do? I hope that everybody has an idea of Ohm's law and how to use it. We will be going into that a little bit more next time, talking about power. And we will start working our way into stuff that you've never heard of. Or ever want to go there. We'll have fun. Okay, well, I'm gonna call the class good night.
Good night.
Right.
Thank you.
Thank you.
Everybody.
Thanks, Joe.
Appreciate
Oh,
it.
you're welcome. And Daron, thank you so much for the great display.
Darren does a lot
Yeah.
with interest.
Oh,
Thanks, Darren.
He'd be a
Thanks,
good
Darren.
source.
Well, you're certainly welcome. I
Okay.
just do what Joe tells me.
I'll reach out to him.